Hello everyone, my name is Karin Wolff and I'm a research fellow from the Cape Peninsula University of Technology in South Africa. As we all know, the nature of engineering work has become more complex with greater demands on engineering graduates. Employer complaints abound about their inability to apply knowledge and solve problems, as well as not having the appropriate technical skills. Now, as educators, we're trying to bridge this theory-practice divide. On the one hand, the exponential development of engineering technologies and contexts complicates the issue of practice, and on the other hand, the theory seems so far removed from what it is that engineers actually do. So my research looks at this relationship between theory and practice in real-world industrial sites. How do engineering practitioners, in this case specifically technicians and technologists, working in 3 different kinds of automation environments, solve problems from the perspective of disciplinary knowledge? How do they work with maths, physics and logic? The purpose of the research is to be able to look back at our curricula and pedagogy and provide input from the field of practice itself. Now, I'll first give you a brief context and methodology overview, and then touch on the analytical tools before comparing 2 case studies. Now, South Africa is a signatory to the Washington, Sydney and Dublin Accords. Our post-school institutions offer 3 types of engineering qualifications: the 4-year professional bachelor's degree, a 3-year Bachelor of Engineering Technology, which is brand new and hasn't been rolled out yet, and a 3-year diploma for the technician route, which is followed by an advanced diploma, 1-year advanced diploma. Now, the problem is not only are we producing 10% of the necessary engineers for a developing economy, but we have only 1.4 technicians for every 1 engineer. Our retention rate and graduation rates are highly problematic, with a 50% dropout rate. But we also have a high number of unemployed technicians as a result of them not having the appropriate technical skills. So it's clear that we're not doing enough to enable the problem-solving engineering graduates we need. My research participants were drawn from 50 employed graduates of a mechatronics engineering program at a University of Technology. These graduates volunteered, and 18 case studies were conducted across 3 types of contexts: small or micro to small contained systems companies. These are research and development or prototyping companies where the focus is on standalone single function devices. Second category is modular systems. These are now machine builders and systems integrators. And the third category is distributed systems, where the focus is on production processes, mainly in manufacturing. Now, data were gathered from an initial electronic survey, participant and company profiles, and video recorded interviews where the participant reenacted how he or she solved a technical problem with the actual components and systems. Now, all these data were transcribed onto a spreadsheet, and references to specific or underlying physics, mathematics, and logic concepts were coded. The idea was to develop problem-solving maps using a range of theoretical tools. The first tool that shaped the research design is Herbert Simon's distinction between the inner and outer elements of an artifact. And each of these elements, the problem solver, the problem environment, problem structure itself, was analyzed with a different set of tools. For today, I'm just going to highlight 2 key analytical instruments from the sociology of education. The first comes from Basil Bernstein's distinction between different forms of disciplinary knowledge. The elements of mechatronics engineering curriculum were analyzed for 3 different types of disciplines. Physics, which is this area over here, the green that you see, is a hierarchical knowledge structure. It has strong concept chains which absorb lower order concepts. Mathematics is what Bernstein would call a strong horizontal knowledge structure. This just means there are different mathematical languages, and each one has specific and recognizable rules, like the difference between algebra and geometry and trigonometry. The third type of knowledge structure is a weak horizontal knowledge structure. Here, like in sociology and the arts, for example, we see several languages of the same kind of discipline, and they're constantly evolving, borrowing elements from other disciplines and each other. There's a lot of redundancy here. And this is like programming, or what I'm terming logic in this research. Now, these three disciplines are learnt in different ways over different periods of time. The question for the research is what happens when they come together in a problem-solving moment? I want you to put that aside for a moment. The second analytical tool comes from legitimation code theory, epistemic relations. Now, this enables us to look at knowledge practice itself, how we approach what. The vertical axis on this Cartesian plane refers to the boundedness of a phenomenon, where strong, here towards the top, means a phenomenon is recognized or accepted by the field as having a particular nature, and where weak means it's ambiguous or contested. Now, the horizontal axis represents the approach to this phenomenon, from fixed on the right-hand side to multiple on the left-hand side approaches. Let's look at the four quadrants that then get set up. The purest quadrant means there's a specific principle that everyone would recognize and its associated procedures, like voltage calculations in a system. The doctrinal quadrant on the bottom right is where it doesn't matter what the phenomenon is. What matters is the method, the procedures, such as the scientific method or applying Six Sigma. The top left is the situational quadrant. This is where there are a number of approaches to a particular phenomenon, like deciding on a control system. Now, the fourth quadrant is either because there's no clear phenomenon or approach, or the practice being observed is not about knowledge, rather about knowers, people in the system. Each of these four quadrants represents a code, a way of thinking. Using this plane, the 18 case studies were analyzed. I looked at how a practitioner approached, analyzed, and solved a particular problem in a controlled electromechanical system, and at which points across that process they drew on actual disciplinary knowledge. These moments were color-coded with green for physics, red for mathematics, blue for logic. And I'm going to contrast two case studies now where technicians solved problems that I mapped the process. Now, technician B1 is a systems integrator. He was called in to solve a problem for a large food processing and packaging company. Bar-coded pallets on a conveyor system were being rejected because the central data management system was not receiving the full barcode. B1 identified the cause as the PC application, written by someone else, is splitting up the barcodes. Now, he didn't do a disciplinary root cause analysis, from a purist perspective, in other words, by analyzing the coding. Rather, he selected the most efficient solution for this situation. He removed the PC, its barcode application, and the cable, and he simply integrated a small communications module with which he was more familiar. Now, B1 has significantly higher academic record in logic-based subjects, programming in other words. This form of knowledge sees an iterative movement between two diametrically opposed ways of thinking, from the multiple possibilities of a particular control situation to the rules of a particular program in the doctrinal quadrant. Now, B1's problem in this context is entirely logic-based. What is connected to what, and what is speaking to what, in what language, and with what rules. So in this environment, this high-pressure production of food and beverages, there isn't the luxury of time for a purist analysis as one might find in R&D, for example. This practitioner's problem-solving strategy reflects both his own strengths and that of the context, which demands highly regulated procedural production of goods. So this is a case of what we call a code match, the right practitioner in the right place solving the problem in the right kind of way. Now, in contrast to this, Technician B5 works at an international machine building company. His problem entailed the integration of a carbonation unit with a new supply pump on a bottling line. Now, when constructing the unit, he observed that the supply pump to the refrigeration unit wouldn't fit on the carbonation unit base frame. His approach to the problem was purist. He started with the purpose of the pump within the carbonation system, then its specifications, and all of this was in typical design report detail. He spent a great deal of the problem-solving process measuring and rechecking the design dimensions, in other words here from a doctrinal insight, before looking at the carbonation unit and pump documentation, which is created by suppliers, hence the knower insight orientation. Then he discovered that the pump could be installed upside down. He finally solved the problem for this situation by deciding to install the pump beneath the carbonation unit frame. Now, in contrast to the first technician, this technician, B5, is a high mathematics and physics achiever, but he didn't do well at all in the logic-based subjects. He spoke of being frustrated at not knowing how to solve the problem analytically, not knowing where to look. He expected a fixed solution to a fixed phenomenon, but his problem needed him to literally think outside of the box. What are all the possible pump positions? Now, these two case studies show how two particular practitioners with contrasting disciplinary strengths solve two different types of engineering problems in the same kind of category. B1 represents a code match. His logic-based orientation enabled the efficient solution to a logic-based problem. B5 represents a code clash for this particular problem. Now, the research data show that solving the problem effectively requires the navigation of different codes across the problem-solving stages over a period of time. Successful practitioners recognize and realize the different code conventions, when to stop and think analytically, when to look at all possible scenarios. The issue here is not that there are different kinds of knowledge and practices in engineering. We know that. Nor that there are different orientations to practice. The issue is the evidence that graduates struggle to apply knowledge when faced with complex real-world problems. And I suggest that such application requires the ability to consciously shift between the different forms. It's the shifting that's not in their curriculum. And it's the shifting that implies a more complex level of practice in 21st century engineering problem-solving contexts. Now, secondly, different contexts demand different ways of thinking. In the research project in question alone, R&D environments tended to see problem-solving patterns concentrated above this horizontal axis, whereas modular systems valued this ability to move diametrically between situational doctrinal quadrants, and large-scale manufacturing and distributed systems environments saw a far greater focus below the horizontal axis. But this is where we're teaching. Now, here lies our challenge as engineering educators. One, we need to make these codes explicit. And in order to do so, we need to understand and appreciate that different disciplines enable different ways of thinking. So we can't just throw out the disciplinary fundamentals. They achieve something else when our graduates move towards integrating knowledge. Now, any single problem-solving moment may offer the opportunity to stop and think. What is the principle here? What are the procedures? What are the possibilities? Who are the stakeholders? And what are the procedures for each of these? Imagine, if you will, one practical example, issuing the same project to an entire class, but providing each group with different functional, budgetary, and contextual specifications. The science at the heart of each project would appear to be exactly the same, but using different sources of power or building to significantly different scales from different kinds of end users would offer an ideal opportunity to make explicit the difference and relationship between theory and practice. Thank you very much.